Greetings to everyone. This video is about a support vector machine linear example. The given problem is, suppose we are given the following data points, that is positively labeled data points 3 1, 3 minus 1, 6 1 and 6 minus 1, and the following negatively labeled data points 1 0, 0 1, 0 minus 1, minus 1 0. So we have to solve this problem using the support vector machine. It is a linear support vector machine because the data points are linearly separable, which means it is easily separable by a straight line. So in order to solve using the support vector machine, we should finally arrive at a hyperplane. So for arriving at a hyperplane, we need a weight vector with values and we require a bias. So to start with the problem, so hyperplane is a decision boundary which clearly separates the data points based on their classes. So for this problem, the hyperplane should clearly separate it as positive and negative data points. So the first step is plotting the points. So we have to plot the given points. So let's start with the positive label points. So I have specified using the blue boxes and I have given it as 1 because it is positively labeled points. And then we have to plot using the red boxes for the negative label points and specify it as minus 1 because those are negative label points. So the first step here is plotting the points, and we have to observe the diagram after plotting, and we can find approximately a hyperplane can be found. So if you divide it at 2, the positive and the negative label points will be clearly separable. So this is our assumption. Let's see whether we can dive into this conclusion at the last step. So considering this approximately this line that is cutting at 2, we have 3 points which are close to these hyperplane. So those 3 points are called as support vectors, which actually helps in the convergence of the algorithm. So the next step would be identification of 3 support vectors. So support vectors are nothing but the data points which are closer to the hyperplane, that is closer to the decision boundary. As for now, we have kept the decision boundary as 2 by seeing only the plot. So with that into consideration, we come into the conclusion that 1 0, 3 1 and 3 minus 1 are the support vectors. So we have to write the 3 support vector. S1 is equal to 1 0, S2 is equal to 3 1, S3 is equal to 3 minus 1. So here plus 1 are specified for positive label, specified by blue boxes. Green circles are support vectors. So in the previous diagram, it would have been specified by boxes, but now the 3 points are converted into support vectors because they are closer to the hyperplane, which we have found using the previous plot. Only by seeing the plot, we have not done any calculations. So with the 3 support vectors, we can proceed with the calculations. So the first step is plotting the points, given points, and after plotting we have to observe the plot and find the approximate hyperplane which clearly separates the positive label and the negative label, and based on that hyperplane we have to find the points which are closer to the hyperplane. Those points are called support vectors, and in this problem we have 3 support vectors which are closer to the hyperplane, and with the help of 3 support vectors we can proceed with the calculation. So step 3 is argumenting the 3 support vectors with a standard bias value, that is 1. So each vector is argumented with a 1 as a bias input. So S1 is 1 0. So S1 tilt is 1 0 1. The final one is the bias. This one is bias. Again S2 is 3 1. S2 tilt is 1 3 1 1. The final one is bias. S3 is equal to 3 minus 1. S3 tilt is 3 minus 1 1. The final one is the bias. So in order to differentiate between support vectors and the argumented support vectors, we are using the tilt. So based on this argumented support vectors, we will proceed with the next step, which is computation of alpha 1, alpha 2, alpha 3. So we have to compute this coefficient alpha 1, alpha 2, alpha 3 because we have to compute the weight vectors, and weight vectors are used to calculate the hyperplane. So before weight vectors computation, in the formula of weight vector we have the alpha value to be computed. So first we have to compute the alpha value. Since we have 3 support vectors, we are computing 3 alpha value, alpha 1, alpha 2, alpha 3. So the calculation of the alpha values, the number of alpha values will change according to the support vectors. In this problem we have only 3 support vectors, so we are computing 3 alpha values. And in order to compute the alpha values, we have a particular equation to be followed, and the equation is given below. So for we have to multiply the argumented support vectors with respect to all the support vectors. So first alpha 1 S1 tilt dot S1 tilt, we have to do the dot product, plus alpha 2 S2 tilt dot S1 tilt. So here in the first equation we are multiplying all the alpha 1, alpha 2, alpha 3 value and S1 tilt, S2 tilt, S3 tilt with the argumented support vector 1, that is S1 tilt. So this is the first with respect to the first support vector. So the first support vector, that is which we have considered here, is 1 0, and in the problem, in the given problem, the question 1 0 is a negatively labeled data point. So since it is a negatively labeled data points, we are is equal to, we are specifying it as minus 1. And in the next equation alpha 1 S1 tilt dot S2 tilt, so we are multiplying all the variables with respect to S2 tilt, that is support vector 2, which is 3 1. With respect to the question, 3 1 is a positive label, so we are putting is equal to plus 1. So we are multiplying the second equation with respect to S2 tilt, that is support vector 2, argumented support vector 2. So alpha 1 S1 tilt dot product S2 tilt plus alpha 2 S2 tilt dot product S2 tilt plus alpha 3 S3 tilt dot product S2 tilt is equal to plus 1. And then the third equation we are multiplying everything with respect to S3 tilt. So alpha 1 S1 tilt dot S3 tilt plus alpha 2 S2 tilt dot S3 tilt plus alpha 3 S3 tilt dot S3 tilt is equal to plus 1, since the support vector 3 is a positive label. So we have to substitute all the values for the above equation, and then we have to do the dot product. So alpha 1 into 101 101 plus alpha 2 311 into dot product 101 plus alpha 3 3 minus 1 1 dot product 101 is equal to minus 1, and then alpha 1 101 dot product 311 plus alpha 2 311 dot product 311 plus alpha 3 3 minus 1 1 dot product 311 is equal to plus 1, and the third equation alpha 1 101 dot product 3 minus 1 1 and alpha 2 311 dot product 3 minus 1 1, alpha 3 3 minus 1 1, dot product 3 minus 1 1 is equal to plus 1. So dot product, we know the formula A dot B. A dot product B is equal to A1 B1 plus A2 B2 plus A3 B3. So it goes on up to an bn. So here we have three values in each vector. So alpha 1 plus a1 b1, so 1 dot 1 1 into 1, so 1 plus 0 into 0 0 plus 1 into 1 1. So this is how the dot product is computed based on the standard formula. A dot product b is equal to a1 b1 plus a2 b2 plus a3 b3 up to an bn. So normal vector dot product plus alpha 2 3 plus 0 plus 1 plus alpha 3 3 plus 0 plus 1 equal to minus 1, and alpha 1 3 plus 0 plus 1 plus alpha 2 9 plus 1 plus 1 plus alpha 3 9 minus 1 plus 1 equal to 1, and alpha 1 3 plus 0 plus 1 and plus alpha 2 9 minus 1 plus 1 plus alpha 3 9 plus 1 plus 1 is equal to 1. So it can be further simplified into a scalar value. So 2 alpha 1 plus 4 alpha 1 plus 4 alpha 3 equal to minus 1, and 4 alpha 1 plus 11 alpha 2 plus 9 alpha 3 equal to 1. 4 alpha 1 plus 9 alpha 2 plus 11 alpha 3 equal to 1. So the final alpha 1 alpha 2 alpha 3 values are computed based on normal elimination methods, and the alpha 1 value is minus 3.5, alpha 2 value is 0.75, and alpha 3 value is 0.75. And we are computing the weight vector, which is summation I alpha I si tilde. So we have to substitute all the weight all the alpha 1 alpha 2 alpha 3 values, and s1 tilde s2 tilde s3 tilde values, and we have to compute the weight vector. So we will finally arrive at the answer 1 0 minus 2. So initially we started with the argumented support vector. So the vectors are actually argumented with a bias. So we have to equate this vector such that the last value, that is minus 2, is the offset bias value. So since we have used the support vector which are argumented by a bias, the weight vector, the actual weight vector is 1 0, and the offset bias is minus 2. So the final hyperplane equation is y is equal to wx plus b, and the standard equations which are provided by Bishop's book for the hyperplane is w transpose into x plus b is equal to 0. This is for the hyperplane equation, and the w value is 1 0, and the bias which we have obtained is minus 2. So since the x is equal to 1, y is equal to 0 with respect to the weight vector, um, we can say if x is equal to 1, y is equal to 0, mostly the line is parallel to y axis. So we have to draw a hyperplane which is parallel to y axis, and the bias value is minus 2, and it will fall in first quadrant. So when you substitute like the weight vectors 1 0 dot x equal to minus of minus 2 actually, so it is plus 2, so on 2 we'll get the hyperplane. Okay, and if the weight vectors are like 0 1, the line will be parallel to x axis, and if weight vectors are x is equal to 1, y is equal to 1, the line will be at 45-degree with respect to x axis and y axis. These are the uh, lines for other cases when x is equal to 0, y is equal to 1, or x is equal to 1, y is equal to 1. But with respect to this problem, it is 1 0, which means x is equal to 1, y is equal to 0, and the line is parallel to y axis, and it will fall in first quadrant. And when you substitute in this equation, you will know like exactly on 2 the bias b will fall. So the hyperplane will be on 2, uh, that is which is parallel to y axis, and it's a hyperplane which clearly separates the positive and the negative. So this is a final last step in the support vector mission computation. So yeah, so yes, thank you.